Hello, this is Aaron Rusk, and I'm going to be walking through my booze assignment part 2 demo. So for the first two sections, I have clicked yes to both of these, and I can demonstrate why. So as you can see, first of all, I've used the standard booze interface wherever appropriate to stay compatible with the library, and as I'm shown here in the app canvas, my drawing class implements the iCanvas interface, and this ensures that all standard drawing commands like rect or line can communicate correctly with my custom bitmap renderer. And second, I declared my own interface to support a unrestricted execution model, which is in the iManual command class. I created this interface specifically to define an execute method that takes an iExecution context as a parameter. So by using a iExecution context interface, which you can see implemented here in the manual runner class, I've decoupled the commands from their main form, and essentially this allows the commands to access the program counter and the variable table safely during my manual execution loop. Moving on to the unit tests, I've ticked yes for all four of these, and I can demonstrate why. As you can see in the Solution Explorer, I didn't just dump every test into one giant file. Instead, I've created separate test classes that match up one-to-one with my main logic classes. For example, as you can see, my manual runner in the Solution Explorer matches with the unit test manual runner in the test files. And if we just open up some of these unit tests, you can see they've been documented with XML comments. And to make sure the unit tests work, we will run all of our unit tests to see if they pass. So as you can see, they've all passed with 0 errors. So next is the factory design pattern, which I've used for all my command generation, so I have marked yes for this one. So if we look at my app command factory class, you can see that I've overridden the make command. And this is where the pattern really lives. So instead of the rest of the app having to figure out which specific class to use, they just ask this factory for a command based on a keyword like if or int. And the way it really works in my project is that the factory checks the current state of the app, and if it's in a unrestricted mode, the factory automatically creates and returns custom classes like app, like for example app int unrestricted. So instead of the standard ones, it keeps the logic for what to build all in one place, which makes it much easier to add new commands later without breaking the rest of the program. So for the singleton design pattern, I unfortunately didn't do this, so that's a no. And for the additional design pattern, I have done this, so I've clicked yes. And so first, the command pattern is the backbone of the whole interpreter. So I'm pointing at the app move to class right now, and each instruction isn't just a line of text, it's a self-contained object that knows exactly how to execute itself. So this made it easier to build the manual runner because the runner in the manual runner just has to tell each object to execute without needing to know the inner details of what the command actually does. So I also use the strategy pattern in my main form, and depending on what the user types or which mode they select, the app chooses a different strategy for how to run the code. It can either use a fast path for simple drawing or switch to my full manual runner for the complex logic. So for this section, I have to show you that I've got the latest boost DLL and show the output in the terminal. Let's go ahead and do that. So as you can see, I've got the boost DLL here, and under assemblies, it's using the boost library. And if we go ahead and run it, as you can see in the terminal, it executes boost and it's using the latest version. So moving on to the variable, I'll begin to show you my int unrestricted running. So if we look at my int unrestricted class, you can see that the goal here was to allow for a limited number of variables, which meant I had to find a way around the built-in restrictions. So when the execute method is called, the first thing it does is to use the parse declaration helper to split the command into a variable name and a value. And if we go ahead and run it, you can see it draws perfectly like the example. So now we are going to test the real unrestricted test. So for this class, this is the class I've used to replace the standard boost real command, and the goal here was to ensure that floating point variables could be declared without any of the built-in restrictions. So if we go to the execute method, the first thing I do here is call the evaluate to double, and this is a critical part of my implementation because it doesn't just look at or for a simple number. It uses the stored program evaluation expression method, and this allows the user to initialize a real variable using a complex math expression. For example, real x equals 10.5 times the factor, and I've used a similar reflection strategy to the integer class. So if we go ahead and test this now, and as you can see, like the example image, it has the same result. So next we'll be testing the array class, and I'll be explaining my code. So in my array unrestricted implementation, I've marked yes because I've replaced the standard boost array handling with my own logic to support the unrestricted storage messages. So as you can see with the check parameter method, my implementation doesn't just look for a simple number when you declare an array. It uses SP evaluation to resolve the size, which means you can declare an array using a variable or math formula like array int mynums, which is a key part of making it unrestricted. And a major difference in my code is how the arrays are stored. I created a static class called array unrestricted, which you can see here, and array store, and instead of relying on the standard library, I use global dictionaries to hold my int arrays and real arrays. And if we go ahead and run the script, we get the same output as the example. So we'll be moving on to the if, while, and for section. So I'll be demonstrating the unrestricted if implementation. So I've marked yes for that section because I've completely replaced the standard if and end classes with my own manual execution logic. And first you can see, to explain how this works, I don't use the standard boost stored program pointer. Instead, I built a control flow map. And you can see the logic. So when this command executes, it evaluates a condition, and if that condition is false, it doesn't just stop, it tells the manual runner to jump the program counter directly to the line number where the matching else or end is located. And let's just give this a test. And as you can see, we get the same output. On to explaining and showing how the unrestricted while program works. So let's jump into it. So if we first look at the control flow map, instead of relying on the simple stack that can overflow or hit limits, I used multiple dictionaries. And these dictionaries were used to map out the entire program before it runs. As you can see here, I have specific maps for while back jump and for forward jump and even else jump. And these dictionaries store the exact line numbers for every starting and ending keyword in the user script. And now looking at the end unrestricted class, this is where the actual jump happens, because this class implements my custom iManual command class interface, and it has access to the full execution context, including the program counter. So for a while loop, when the runner hits the end line, when the execute method looks at the while back jump command map, it finds the original line number of the while command and resets the PC to that line, which forces the interpreter to go back and reevaluate the loop condition. And for a loop, it does something even more advanced. It finds the matching for unrestricted command and calls an advanced method to increment the loop counter. And to show that this works, we'll do the test. As you can see, the image draws successfully. Onto the for loop. So I've ticked yes because I've got the unrestricted for loop implementation working. So if we go to the for unrestricted class, this class is built to handle three distinct tasks, which are initialization, condition checking, and finally stepping. So when the manual runner hits the for line, the execute method um, initializes the loop variable and then sets the limit. And if the condition is already met, it uses the control flow map to jump straight to the end. And the unrestricted part happens through the interaction between the for command and the end command. So if we get the program running, as you can see, the image is the same as the displays. So essentially, my for unrestricted implementation manages loops through a combination of initialization, logical, and a manual advanced method. And the end restricted command triggers the increment step and uses the control flow map to reset the program counter to the loop start. So I have ticked yes for the else implementation because I've got it working. So we'll check the logic behind it. So essentially else works unrestricted in my interpreter using my own code. As you can see in the app command factory, when mode is unrestricted, the keyword else maps to my else unrestricted class, and my control flow system, this builds matching if else end links using the real source line numbers at runtime. Manual runner executes line by line using PC. So if the condition is true, the runner skips the else block, and if the condition is false, the execution jumps to the else block. So I'll now run the unrestricted if else example and show the output matches the provided reference image. So lastly, we'll be going on to the unrestricted methods. So I've marked this yes because I replaced the standard method class with my own system that handles definitions, parameters, and return values. So if we go to our code, as you can see in our manual runner class, this handles methods by performing a pre-scan of the source code. It then identifies the lines between the method and end method keywords and stores them in a dictionary of method def objects, which I'm pointing to now. And because these blocks are indexed by line numbers, my manual runner knows to skip over them during execution, so the method doesn't run until they're actually called. So when the interpreter hits a call command, the call command class takes over. It looks up the method in the dictionary, maps the passed arguments to the method parameters, and then tells the program counter to jump to the start of the method's code. So if we give this a run, and as you can see, we've got the output we have wanted.